Hello, my name is Zing Zhang. I'm an undergrad researcher working in Dr. Ganchun's lab. Today I'm here to present to you the project called One Step Improving Synthesis of Monodispersed Gold Nanorods with High Uniformity. As you know, gold has been regarded as one of the most precious matters in the world since its first extraction in the 5th century BC. It becomes more precious when it is divided into fragments of size reaching down to 100 nanometer. The metal is the most precious material since early days in human civilization. Gold is one of the least reactive elements, which makes it solid or tangible to hold under standard condition. Therefore, gold has been used as a worldwide currency as well as a symbol for high class and high social status since ancient time. The noble metals' optical properties have been applied for spherical gold and colloidal silver synthesis back in Roman and Chinese empires. It is only 20 years ago that scientists have broadened the knowledge that they can in fact create, control, and reproduce anisotropic metal nanoparticles. Since then, the optical features that rely on shapes of the anisotropic metal nanoparticles have been appreciated and studied extensively. The nano semiconductor wires synthesis by vapor liquid solid method was introduced in the 1960s, and metal nanorod colloidals were synthesized not until 1990s. Due to the unique plasmonic properties, gold nanorods are the most attractive to a wide variety of applications. The aspect ratio of the nanorods can be controlled so that the longitudinal surface plasmon resonance is altered. So because of that surface plasmon resonance is being altered, these features can be applied in so many applications, such as applied in electronics, optics, catalysis, and drug delivery, and so many other real-life applications in medical field as well. There are several methods to synthesize gold nanorods, such as photochemical, electrochemical, and most commonly seed-mediated synthesis. Due to the simplicity and economical advantages, as well as a high-yield, smooth morphological result, seed-mediated approach was appreciated and developed extensively in the field. As you can see, nanoparticles can be classified into different types according to size, morphology, physical and chemical properties. Some of them are carbon-based nanoparticles, some of them are ceramic, some of them are metal, semiconductor, polymeric, and lipid-based nanoparticles. But today, we only focus on nanorods classification of the whole nanoparticle field. Various nanorods have been extensively studied, such as carbon nanorods, zinc oxide nanorods, gold, and magnetic nanorods. It varies from 10 to 120 nanometer. Recently, various techniques have been proposed for synthesizing the nanorods. It can be classified into either via physical or chemical methods, or known as bottom-up or top-down methods. So why nanorods or gold nanorods are so widely applicable in the field is because of its LSBRs, or is called as localized surface plasmon resonance. Those are the electron oscillations that are coherently delocalized, occurring when dielectric molecules have sign changes at the interface of certain materials, such as metal dielectric interface and metal sheet that put out in the air. Surface plasmons require a lower energy than bulk plasmons, which essentially calculate the positive ion cores of the longitudinal surface of electron constellation in the electron gas, or also as known as plasma. Surface plasmon charge motion can generate electromagnetic fields outside and inside the middle. The total excitation containing both the charge motion of the surface plasmon and the generated electromagnetic field is named surface plasmon polar region for planar interface, or a localized surface plasmon regarding closed surface of small particle. While surface plasmonic resonance (SPRs) is an experimental technique that measures the maximum of the surface plasmon by examining the reflected light from the prism coupler as wavelength. This method can be utilized for monitoring thickness, density, molecular absorption changes in nanoscale. So that's why nanorods have been so widely applicable. Despite all the mentioned positive feedbacks and results, there are some perspectives that the approach can improve, as gold seeds stability are very time sensitive. The reproducibility rate is rather low, the aspect ratio cannot be controlled and only limits to 2 to 5. The reduction of gold ion is also low, and the width measurement of the rod is longer than expectation, which is, aspect ratio in there as well. That's hard to control, and especially the uniformity is very low, which is what we focus on today. As you can see in the picture up there, in these two popular approaches, the mechanisms are similar in the following way, and it is a typical explanation and typical mechanism of how gold nanorods are synthesized. So first, the preparation of seeds by reduction of gold precursor by a strong reducing agent, typically a sodium borohydride. Second, a preparation of gold solution containing partially reduced gold precursor with the help of a weak reducing agent, typically ascorbic acid, or in our case, we use hydroquinone. And third, a growth nanorods by addition of seeds in the growth solution. The use of weak reducing agent like ascorbic acid or hydroquinone instead of a stronger agent like sodium borohydride in growth solution arrests the tendency of nucleation in the growth solution and thereby facilitate the growth of the added seeds. The most common approach to obtain high quality of gold nanorods is the seed-mediated growth approach. A conventional method entails the mixture of gold nanospheres that are situate capped, acting as seeds to gold chloride growth solution. The seed solution normally involves cetyltrimethyl ammonium bromide, or we can call it CTAP, as a surfactant, and a gold salt. In here we use gold chloride and sodium borohydride as reducing agent and increasing the overall ionic strength of the reaction. The gold solution is typically involved with the reduction of gold chloride by reductants such as ascorbic acid or hydroquinone in our experiment, with the presence of CTAP served as surfactant, and silver ions, typically silver nitrate. Silver, compared to gold, has a lower reduction potential and forms a monolayer on the surface of the gold rods. This deposition slows down the growth rate of crystal facets, give orientation to one-directional growth of the formation of rods. The high uniformity synthesis in this article involves adding silver ions or silver nitrate to the seed synthesis that help with the one-directional growth from the beginning, resulting in a rod instead of sphere formation in the seed solution. The end results of seeded growth, size, and shape distribution of the nanoparticles, and therefore their optical responses, are sensitive to every ingredient and parameter that can be altered. The fundamental parameter aspects that we have been tackled are temperature, time, pH, and concentration of the reactions. Herein, we tackle one of the fundamental issues of gold nanorod synthesis, uniformity. From the UV-vis spectrum we can easily tell whether the rods are uniform or not by the full width at half maximum of the longitudinal surface of the rods. As can be seen from the figure, absorption in green in the absorption illustrates gold nanorods in which lower transverse peak at 512 nanometer depicts a transverse peak, while a stronger peak at 780 nanometers shows a longitudinal mode. Adapting Gaussian distribution theory, the narrow and taller the longitudinal peak it is, the more uniform and the more uniform the rods would yield. So full width half maximum of the absorption is measured to determine the uniformity. After many trials and errors, these are our results. We did a seed solution, we optimized the seed solution with the variation of freshly cold prepared sodium borohydride. And as you can see from the left, 10 microliter of the sodium borohydride has the least or the lowest value of full width half maximum at 143 nanometer as compared to other variation of sodium borohydride. From addition of 50 microliter of sodium borohydride and up, the seeds or the mini nanorods at this point were no longer formed since there's no sign of longitudinal peak around 780 nanometer. Instead, strong peaks of transverse peak was shown at 512 nanometer, indicating spheres particles. According to 25, the trial with the 25 microliter sodium borohydride solution, longitudinal peak was formed, but transverse peak was very high, indicating its low yield and less uniformity. Therefore, an optimal amount of sodium borohydride is proven to be at 10 microliter. While on the right side of the slide, we can see the UV-vis of the growth solution with the optimal seed solution on the left, which we use for 10 microliter. The second step, synthesis of a full-grown nanorods with variation of nanorod solution show in the UV-vis spectrum that yield rods with both transverse and longitudinal peaks. The full width half maximum is 95, 91, and 92 nanometer. In respect of the variation of the seed added, which is 0.1, 0.25, and 0.5 milliliter respectively. And all of the value of the full width have maximum under 100 nanometer, which is considered to be really uniform. As you can see, all of the solutions of the trial yield rods with both clear shown transverse longitudinal peaks. And in this experiment, we use, as you can see, the ratio of the seats and the C-tab used. For example, on the top, we added 7 milliliter of C-tab and 3 milliliter of the seats. Down there is 8 milliliter of C-tab, 2 milliliter of seats, and 8.5 C-tab, 1.5 to the seats, and etc. etc. So as you can see that all of the solution of the trial yield rods with both clear shown transverse and longitudinal peaks. However, there are two longitudinal peaks of the 9 milliliter to 1 milliliter of seats and the 9.2 C-tab milliliter to the 0.8 seats instead of 1. This occurrence can be due to the wide range of aspect ratio leading to uniformity of the results, or perhaps due to the pipette transferring and technique errors. Although the full width half maximum was under around 100 nanometer, specifically 98 nanometer, 108 nanometer of the value respected to the 9.7 and 0.25, as well as the 9.5 and 0.5 C-tab and seat respectively. The results were not trustworthy. Errors were confirmed by the repeated trial, and the shifts are all consistent, but there were no two peaks of any solution, which means that the transferring technique needed to be improved. From repeated trial, we see the peaks were consistent and show nanorods around 780 nanometer, but most of them were not able to show reactions of rods, so they were not able to be normalized. However, the 9.9 milliliter C-tab to the 0.1 milliliter of seat ratio has a full width half maximum of 98 nanometer, which is under 100 nanometer, and that was normalized correctly and shown uniformity. After repeating the reactions, although the shift and peak wavelengths are consistent, it is hard to reproduce the trial. As you can see on the right side, the TEM image of the 9.9 milliliter of C-tab to the 0.1 milliliter of the seat verified that the result was indeed uniform, although its aspect ratio needs to be improved. So by conclusion, uniformity indicated by full width half maximum of gold nanorods can be tuned by variations of base reagents, nanorod solutions, and different ratio of the nanorod and C-tab reagents. The reproducibility has always been a fundamental issue in the gold nanorod synthesis, and these trials are not exceptions. The trials and errors needed to be proceeded further to improve reproducibility, and techniques in the synthesis is yet to be developed and practiced furthermore. These are the references of the sources of the references that I used during this presentation. I have this special thanks to Dr. Gang Chen that gave me the opportunity to learn a lot in the lab for the past years and helped mentor me through this project, as well as thank yous to Dr. Zing Zhang that also mentored me a lot and supervised me and helped me answer a lot of the questions. And Reese Gallagher, who is not in UCF anymore, but he was one of the best mentor out there that I like to thank. Mm, and thank you so much for listening. Thank you.